Hello my physics friends, this video is about magnetic force on current carrying wire. There is this beautiful video on the book. It's also in one of the problem sets or the pre-lecture assignments. You'll watch it. That if you have a current passing through a wire, this is a tungsten filament, and you can see the wire is oscillating because of magnetic. And if you put a magnet close to it, you'll see wire is oscillating because magnets attracts the current. So if there's a current and there's a magnetic field area around the current, magnetic field will apply a force to current carrying wire. And we will find the direction of the force using the right hand rule, as I call it, right hand rule 3. Very similar way to we use to find the force applied to a moving charge. In this case, we're going to put our fingers first along the current and then curve them towards the magnetic field and open our thumb. As you see in this figure here, our thumb will be showing the direction of the force. If I apply that to this guy over here, I have an upgoing current, so I'm gonna put my fingers and arm up first, and then I'm gonna roll my arm so I can curve my fingers towards the magnetic field. I'm doing my best to draw this here. I know it's not perfect, but into the board here. Open my thumb will be showing the direction of the force. So current, magnetic field, this is into the board, and force is to the left as shown in this figure here. So that's the idea here. The same thing we have here when we apply right hand rule. I put my fingers along the current, curve them into the board because magnetic field is into the board here. Open my thumb as I do that, and my thumb will be showing the direction of the force as we see in this figure here. Fingers curving towards the magnetic field and the thumb. Finding the magnitude of the force will be a simple matter. Current times length of the wire that is inside the magnetic field times the magnetic field times sine alpha. If alpha is 90, sine alpha is 1, so we'll end up getting this equation here. Let's apply right hand rule to this figure here. Positive charge and a current into the board, magnetic field is upward. So I'm going to put my arm and hand along the velocity first. And I'm going to curve my fingers upward. That's the magnetic field. As I do that, I should roll my arm, open my thumb. As I open my thumb, I will see that my thumb will be out of the board. So the force on this charge will be out of the board. I hope you can imagine this, or do this with your hand. Will be a better approach here. Board or screen. For the current carrying wire, it's very hard to draw it because I have to put my fingers and arm into the board here. So please do it yourself as you listen to me. Put your arms into the board here and in the direction of into the board, and then you're going to rotate your arm to curve your four fingers upward. Once you do that, when you curve your four fingers upward, your arm is into the board. Open your thumb, you will see that I'm trying to draw it a little bit, but it's not easy. Your arm is into the board, curve upward, and open your thumb will be showing the direction of the force. The force should be to the right here. So again, let's do it. And with your arm, right arm, put your arm towards into the board direction. Rotate your arm and curve your fingers upward because magnetic field is upward, and open your thumb. That's going to be to the right. Using the right hand, we can find, knowing the force. We see the forces here in this picture. What is the direction of the current in the loop? Since we have a repulsion, when I find the magnetic field direction for my loop, I'm gonna have a symbolic magnet that will has its south side there and north side here because of the repelling forces. So that means the magnetic field in the center should be to the left. I'm going to apply my right hand rule 2 this time. Looping current, I loop my fingers along the current. My thumb shows the direction of magnetic field. Now I know the direction of magnetic field. I'm going to put my thumb along the magnetic field, curve my fingers after that. I will see that the current should be into the board here, out of the board there. So it comes out here, turns back, goes back in to the board there. That's the direction. At the top, in at the top, out at the bottom would be our answer here. The horizontal wire can be levitated, held up against the force of gravity by a magnetic force. That means the magnetic force is upward. What is the direction of current? The current in the wire is to the right, left, and it can be decided are our options here. So I have to put my arm along the current, and as I do that, I should be able to keep my thumb upward because the magnetic force is upward, and roll my fingers into the board. So I'm going to try to the right first. If I try to the right, I put my arm and fingers along this direction and curve my fingers into the board. I can do that now, and as I do that, am I able to see that when I open my thumb it's along the force direction? Yeah, so then this should be the direction of the current. So kind of walking backward here. If I assume current is to the right and curve my fingers toward magnetic field and open my thumb, is it upward? Yes, then that's the direction of the current. So the current direction is explained as from left to right, which is the direction we found. This question is involved in finding the magnetic field, knowing the force. We are given that we have a current carrying wire. Current direction is actually given here. Magnetic field direction is not given. And that current carrying wire is applied a force by a magnetic field, background magnetic field, direction of which we don't know. And that force is equal to 4.2 times 10 to minus 4 Newton. The part of the wire in the magnetic field, which is L in our equation, the length that is in the magnetic field is 50 millimeters. That's 50 times 10 to minus 3 meters. The current through the wire is 30 milliampere. That's 30 times 10 to minus 3 as well, amperes. What is the value, magnitude, and the direction of the force magnetic field? And this figure here nicely shows the right hand rule for this question. I put my well, kind of. I would put my arm along here to see it better, but it's alright. A hand and the four fingers, I put them along the current first, right? And as we roll them, it's the same as the previous question. As we roll them into the board, open our thumbs. Is it upward, which is the direction of force? Yes, then the current should be to the right. So find in the direction, sorry, the magnetic field should be into the board. We know the current direction. So the magnetic field should be into the board because our thumb is along the force. So again, let's do that here again. We know the direction of current, so we put our fingers and hand along it. The figure is nicely showing it too, but I would put arm along the current too to make it more clear. And then as I do that, I want to have my thumb up. So I rotate my arm and have my thumb up because the force direction is that. I know that. And this is the current direction. And then when I roll my fingers after I arrange my arm, so the thumb will be up. When I roll my fingers, that will give me the direction of the magnetic field. So it should be into the board. So magnetic field is into the board. And how we find its value, we know that the force is equal to current, length of the wire inside the magnetic field, times the magnetic field, times sine alpha. And from there I can solve for magnetic field. In this case, our alpha is 90 again. So sine alpha is 1 and it's dropped. Then we solve for magnetic field. It turns out that if I have two current carrying wires together, they have their own magnetic field and each will apply a force to the other one. I can find the force direction using right hand rule. For example, here the same direction currents. This guy will have magnetic field in this fashion from the right hand rule 1. So into the board here. We call this B1, that B1 will apply a force on this guy. So the magnetic field into the board. When I apply my right hand rule and I put my four fingers along the current first, right? Then I roll them towards the magnetic field, which is into the board. As I do that, I arrange my arms so I can open my thumb, and that will be showing the direction of the force would be to the left. And what we will find that these two current carrying wires will attract each other via their magnetic fields. Then we can drop the idea of finding the direction using right hand rule and so on, and we can just go ahead and say we have two current carrying wires, they will attract each other. The force will be coming from ILB sine alpha. When we put in all the values, the magnetic field value due to one current and the other current will be the force applied and so on. What we will find that they will have equal and opposite forces. These are actually action-reaction pairs. So equal and opposite forces. And we can write down the equation in this format. It actually comes from the force applied to one wire is equal to the current of the wire, length of the wire, times the magnetic field of the other wire. So if I call this F for 1, so it will be I1, L1, but B2 because the force is applied by the current 2 then. And it will end up giving us this equation. So we don't have to really spend too much time in there. We'll just go ahead and use this equation. If I go by the same idea, find the direction of the forces using right hand rule 3, I'll find that the currents in opposite direction will repel. Equation for the force is the same as this equation. And that's all we need to know about that. This question here is giving us the value of currents, length of the wires, distance between them, and asking us what is the force between them, what is the direction, what is the magnitude. Magnitude mu0 I1, I2, L divided by 2 pi D, and they're opposite directions, so they will repel each other. That's the direction. So this case is an easy case for forces due to current carrying wires on each other. And once you apply and put in all the values, you'll find force to be 1.4 Newton. I could go ahead and find the magnetic field of one of the wire and then use ILB to find it. I would find the same result. This one is showing you the approach to use and find the values. How I summarize this, as always in class, is to draw a picture to help you. Find the direction of the force first, then find the magnitude, which will be a simple matter with using an equation. Over here on this forces between loops, I don't want to go into too much details. We could, but eventually what we will find is that if the loops are carrying currents in the same direction, just like the straight wires, they will attract each other. So these will be the forces, attractive forces. And if they are carrying current in opposite direction, this guy is carrying current up and this guy is down, they will repel. And why does it happen? We can explain using right hand rule 2. Remember, we roll our fingers along the loop, open our thumb, that shows the direction of magnetic field. We find that magnetic field direction, let's call this B1, and then we can assume there is a bar magnet in the center of the loop, and we have B1 in this direction. This will be north side, this will be south side, because the magnetic field of the loops is very similar to bar magnets. Do the same for this here. Rolling my fingers along the loop, right hand rule 2 again, opening my thumb. I'll find that the magnetic field is into this direction in the center, so this will be the north side, this will be the south side then. And then north-south will attract. If I want to go for more details here, I would say always remember magnetic field of a bar magnet away from the north towards the south, and I can complete it here. But they will attract each other because south and north sides. I can go this way, but again, I don't have to go too much in detail. Simply I can say same direction forces attract, opposite directions repel. This figure here is asking what is the force on the loop on the right. As we see here, current in here and out there. These guys kind of loops here, and both have currents coming out of the board here, going back in there. Okay, let me try that again. So current, they draw them straight on. It's hard to explain, but out of the board into the board. This guy is the same, out of the board into the board. So same direction currents. That's all I'm trying to show here. And what they do then, let's call them I1, I2, attract each other. Same direction currents attracts each other. The right guy pulls on the left guy, and the left guy pulls back on the right guy. The force on the one on the right is to the left. This question is a nice question here. We have 10 centimeter long parallel wires. And there is 5 millimeter in distance in between them, and they are in a circuit, simple circuits, both of them. There is resistance and the wires. For what value of resistor R, the force between these two wires is 5.4 times 10⁻⁵ Newton. This is a very beautiful question involving circuits, finding the currents using Ohm's law, and involving the magnetic field generated by a current carrying wire and wires attracting or repelling each other because of that magnetic field. First, let's see, we know the force value. Let's put it down here. Uh, 5.4 times 10 to minus 5 Newton. Let's see if they will attract or repel, and that we will say by finding the current passing on the wires on the left and right. In the first system here, I'm going to call this system 1, maybe current I1, this will be R1. I'll leave this as R because it's given as R, but I'm going to call the current here I2. And so on. As they continue, we will see that I1 will be going down on the left and I2 will also be going down. Same direction, so they will attract each other. If I was asked to find the direction of the force, it will be to the right on the left and to the left on the right. It's very small, hard to show, but that's the force. And they are equal to each other, opposite in direction. Let me do that actually. I'm going to show them at different points. So this guy is pulled to the right with force F, and this guy is pulled to the left with force F. How will I find that force? I know this equation, mu 0 I1 I2 L over 2 pi d. L would be the length of the wires, either one. Alright, what do I know here? Constant. Current one, I don't know, but I know how to find it. Apply Ohm's law to this first circuit here. I1 is equal to delta V1 over R1, and my delta V1 would be 9 volts, right? So 9 volts divided by 2 ohms, R1 would be that guy, 2 ohms, 4.5 amperes. I don't know I2 because I don't know R here, which is what I'm looking for. I know L, the length of the wires, 10 centimeters, so L is 10 centimeters, 0.1 meters. And I know D, the distance between the wires, 5 millimeters. That's 5 times 10 to minus 3 meters, not 55. So what I can do, I'm looking for R, and here is my plan. I can find I2 from here, right? I know all the rest. And how do I find R? Applying Ohm's law here. I2 is equal to delta V2 over R. I know delta V2. And from here I can solve for R. I can say R is equal to delta V2 over I2. Insert this guy, insert that guy, find R. So first duty is to find I1 from here, insert there to find R. Not I1, sorry, I2. As we do that, we will use the I1 value we found here. So first what I want to do is I want to solve for I2 here. I'm going to do cross multiplication. I would have 1 here. So that would give me mu 0 I1 I2 times L is equal to 2 pi d times the force F. And then I divide each side by mu 0 I1 times L. Then that will give me my I2 because all these will go, right? So I2 is equal to 2 pi d times F divided by mu 0 I1 times L. Input in all the values here. I will find that current 2 is equal to 2.99 amperes. Inputting that in there, I will find my R to be about 3 ohms, 3.01 ohms. See you in the next lecture.